I am François Gérin, chairman of SEE and part of the organizing committee of Jicable 19. And on the behalf of this organizing committee, I am very pleased to welcome you for this exceptional conference, which shall be given by Dr. Bernard BIGOT, CEO of ITER organization since 2015. And Bernard has a lot of experiences in the area of physics and chemistry and big projects. He was Chief of Staff to the Minister of Research and New Technologies at the beginning of the year 2000, High Commissioner for Atomic Energy between 2003 and 2009, High Representative for the reception in France of the ITER program, which was a very important, not only technical, but also diplomatic action between 2008 and 2015, and CEO and chairman of the board of the Atomic Energy and Alternative Energies Institute, CEA, between 2009 and 2015. And I shall give him the floor to present this very interesting project, which might be the starting point of a new future for energy in the world. Bernard, you have the floor.
So thank you very much, François. I am so pleased to have opportunity to be with you. Thank you for attending. And so I guess I will be ready to start the presentation. Indeed, this project is quite large. And as you see, is gathered now more than 35 nations which are committed to join their best effort in order to offer to the world the option of hydrogen fusion. So you see on this slide, it is an aerial view of the ITER site. It's a large platform, nearly 50 hectares, 1 kilometer long, 500 meter large, where you have what we call the tokamak, where we expect to fuse hydrogen and produce 10 times more energy we will feed in at this time. The challenge, it is a research project. This research project intends to open the way to a new, clean, safe, and nearly unlimited energy, and I hope I will convince you it is not just a dream. Maybe it would be one of the biggest challenges of our civilization. I am sure you are aware that we are nearly 7.5 billion inhabitants on Earth. I see very recently by 2050 we expect to be 10 billion. And I'm sure also you understand that in order to make these people living according to the best standard of life, they need energy. The world has relied on renewable energy only up to the end of the 18th century, when we discovered what we call the fossil fuels. At that time, because they use only renewable energy, the world population was limited to 1 billion of inhabitants, scattered all over the world, and the expectation of life was below 35 years. Why? Because in order to get their energy, the people has to rely on renewable, and renewable is dispersed, is diffuse energy, as you know, of the order of 100 watt per square meter at the best, except maybe during the next week, where we expect to have a very hot temperature. And second, you have to make a lot of effort in order to get your energy available. And so ITER tried to offer a new option. I will explain to you in detail. This view is just what we call the tokamak pit, where we will be able to fuse hydrogen. This project is so large and challenging that indeed we need to set up a multinational scientific collaboration maybe without equivalent in history. As you see, the 7 ITER members representing 35 different countries, indeed 6 non-European countries, which are China, India, Japan, Korea, Russia, and the United States, plus the European Union, plus Switzerland, and altogether they commit to join their effort in order to demonstrate that the phenomena which is so familiar in the world, indeed in the universe, which is hydrogen fusion, we could control it on Earth and make the best of it in order to provide energy. I am sure you are aware the star and the sun are mainly hydrogen. For example, the sun is a big bubble of hydrogen, 300,000 times weighting more than Earth. At the center of this big bubble, you have what we call a very hot, dense plasma, 15 million degrees of hydrogen plasma, and under the forces of the gravitation, you force the hydrogen nuclei to get closer and closer, and when they get so close, they fuse. They fuse, and they produce 2 new particles, an helium nuclei and a neutron. And these 2 particles get out with a large increase of energy. I am sure you understand that it is not so easy on Earth to gather 300,000 times more weight than the Earth. And so the physicists had to decide to choose a fully alternative route. The route is to use a very low density plasma. The density of the plasma will be 1 million less than the density of the atmosphere. And in this condition, you are able to accelerate the hydrogen nuclei to such a speed that when they will collide, they will fuse. In the sun and the star, the kinetics is very slow, fortunately. The sun, for example, is shining for more than 5 billion of years, and it will be shining again for 5 more. But the reason is mainly because very few collisions are efficient in the sun. Here we expect to have a high yield of collision. How could we do that? It's quite simple. You just use magnetic forces. We will build a huge magnetic cages, and I'm sure all of you know very well, when you have an electrical particle nearby a magnetic field, the electrical particle is captured by the magnetic line, by the magnetic fields, and spin around the magnetic line, continuously accelerating. Everybody could understand. If you have a high vacuum, no neighbor nearby, you have time to accelerate before you collide with the neighbors. And so is why we need quite a larger size in order to have the time for acceleration. You start with a very low speed, and you get up to a speed which is equivalent with 150 million of degrees, 10 times the temperature of the sun. In this condition, when you collide, and indeed we use a special brands of hydrogen, the most efficient one are the 2 isotopes, maybe you know, deuterium and tritium, and when they collide, after you accelerate them, they will produce, as in the sun, the helium nuclei and the neutrons. And as you see, when they collide, the equivalency of the temperature of 150 million of degrees is 0.1 million electron volt, and you get the helium which go away with 5 times more energy, and the neutrons 20 times more energy. How do we collect now this energy? It's quite simple. First, this helium nuclei is still at this temperature electrically charged. It will stay within the plasma, and it will heat up the hydrogen. You will feed continuously the hydrogen in the plasma, and so is why we say we have a burning plasma. It's nearly a self-sustained plasma. And when it will have reached the same temperature as the hydrogen, you will pump it out, and you will get still the remaining energy. It's quite a large part of energy you have to think about that they will collide with what we call the divertor, which collects the helium with an equivalent of 20 megawatt per square meter. Very high, flux of energy. Second, you have the neutrons. The neutrons will escape from the magnetic cages because it does not suffer in any case, the magnetic field, and it will collide with the wall of the vacuum vessel, and like a bullet on a steel plate, it will be abruptly slowed down, stopped, and it will transfer its kinetic energy to heat. It will heat up the wall of the vacuum vessel, and you will collect this heat with water, produce a steam, and make the turbine producing electricity. So the principle is quite simple. I say tokamak is just a boiler. It's a special boiler, but quite efficient. And you have to know that, for example, when 1 gram of hydrogen is fusing, is equivalent if you are burning instantaneously 8 tons of oil. The record made by the Joint European Torus near Oxford in the UK, where in 1997 they have been able to produce 16 megawatt of fusion power, but only with a yield of 0.65. You feed more energy than you get out of it. So it is in this condition that several large countries, indeed in 1985 it was the US and the Soviet Union at that time, they decide to join their effort in order to build a sufficiently large machine in order to demonstrate what is fusion possibility. So they launch a large international research collaborative program, and they request everybody which will be willing to join to join the program. Immediately Europe and Japan joined the program. During 15 years, many engineers and scientists have designed the machine, and around 2000, they considered that the program was mature enough in order to think about governance, cost sharing, and location. As always in that case, there is a long debate and discussion. Immediately China and Korea join us, and indeed in 2005, the 6th initial partner, India, joined on the same day, agree to move on, and decide to have it located near Aix-en-Provence in France. So, as you see, we start in January 2007, just deforesting a small hill near Aix-en-Provence. The platform was ready in 2010, and now we are moving on and on. So, again, I repeat, it is a global challenge, and we need a global response. Is why in June 2005 at Moscow, the ITER members unanimously agreed to build ITER in Europe, and the agreement was signed in 2006 for 42 years. And the 7 ITER members represent more than 50% of the world population and about 85% of the global GDP, and I'm sure you recognize all the partners. What a tokamak is, and what we have to build. It's a cut of the tokamak. You see, this cut is a cut of the torus. The torus has a volume of nearly 1,800 cubic meters. It is made of stainless steel, and it is nearly 20 meters high and 9 meters large, like this one. At the center, you will have the plasma not touching the wall, because around the vacuum vessel, you have 18 what we call vertical or toroidal coils made of superconducting materials, 6 horizontal ones, what we call poloidal coils, and this central solenoid. And these coils are superconducting, and they have to be cooled down at minus 269 degrees. You could imagine here you have the plasma, a tube, not touching the wall, 150 million degrees, and a few meters away you have the lowest temperature you could expect, minus 269. It's the largest gap of temperature in the universe which will ever happen. And in order to save energy, we designed and built a huge box, indeed what we call the cryostat. It's like a thermostatic box. The box is a 30-meter diameter, 30 meter high. All this piece we have to assemble in what we have mentioned in the very early slide in the tokamak pit is weighing 23,000 tons. And because it is made in France and everybody know about the Eiffel Tower, it's, you have to think about you put 3.5 Eiffel Tower in the box together. So we start, we have the agreement. And all the 7 members consider that if fusion is working, and we work very hard in order to make it happening, it will be a real industrial breakthrough. And so all the members want to train their best industrial champion in order to demonstrate that they could deliver all the piece. So it has been agreed to have a share among the 7 members, which will provide in kind the component. To be frank with you, it is not the best way to lead a project like this, but it was a prerequisite. And so 90% of the cost of the construction will be provided in kind by the 7 members. So we have 7 what we call independently, legally domestic agencies in charge to pass the contract with their industry, and the ITER organization which is in charge of integrating, and it is exactly what I am heading now as ITER Director General or CEO, as François has said. And so in the joint ITER agreement, which was signed in 2006 at Élysée Palace, they decide the breakdown of the various in-kind contribution. And they decide that all the 6 non-European countries will provide each of them in value 9% of the construction, and the Europe 5 times more. So you could imagine, let's take an image. You want to build a car, and you decide that one wheel will be made in Japan, the second one will be made in Korea, the third will be in Russia, and so and so. So it's quite a challenge, but I guess if we succeed, it will be a good demonstration that there is goodwill and work together, we are able to succeed. I just repeat, ITER mission is clear: to demonstrate the scientific and technological feasibility of fusion power for peaceful purpose, evidently. And so we do that with magnetic fusion device, and we expect to feed in on a steady state 50 megawatt of heating power to the plasma, and the plasma will produce 10 times more minimum, 500 megawatt, and it would be a clear demonstration. How it works? Again, it's quite simple in some way. You just start to make the vacuum in the huge vacuum vessel chamber. A lot of pumping to do that. Once it is with the proper vacuum, you inject 2 grams of the fuel. Immediately you make an electrical discharge to create what we call cold plasma, is any bump you may have in your home. And due to the fact that this cold plasma is embedded within the magnetic cage, they start accelerating. And very soon you have a 15 million ampere plasma current. And due to Joule effect, it's heat up. Very soon you will get around 100 million of degrees. You need some extra heating. It will come from electromagnetic waves, as the equipment you may have in your kitchen. We inject some high-energy neutral particles, and as soon as we get the 150 million degrees, fusion starts, and in that case, it is sustainable. So, I just want to repeat, size matters. You see the world record by the jet, the volume of the plasma is around 80 cubic meter. ITER expects to have a 10 times larger plasma volume. The heating system in the jet is 23 megawatt in order to get only 16 megawatt of fusion power, with the ratio of 0.65 as I showed quite recently. In our case, we will double the heating power, but we will get 30 times more fusion power. Size is absolutely critical. And you understand why. It is to have the time for the acceleration. If you have not the time for acceleration, you collide too early, and no fusion could happen. So the critical component of these devices is the magnetic cages. It will be the largest magnetic cages ever built. As you see, with the 18 vertical coils, the 6 horizontal one, and the central solenoid. The size of the magnetic cages is around 20-meter diameter, 20-meter high. You see the size of the fellow. It's like if you have a building with 7 floors. The challenge is we have to assemble all these coils with a precision such that the magnetic axis of the magnetic cages has to be positioned with a precision below 0.5 millimeter. Why? Because with the very high speed, if the magnetic lines are not perfectly shaped, the particle will escape. You need to weigh very precisely the magnetic line in order to capture all the particles properly. So the big challenge is really this one. We have to assemble nearly 10,000 tons of superconducting magnets. These magnets are manufactured from niobium tin or niobium titanium. As I explained, they will become superconducting when cooled down at minus 269. And you see the magnetic energy in the coils will be over 50 gigajoule. Very, very high energy. We do it with the largest superconducting procurement in history. The building block of the magnet system are high-performance, internally cooled superconductors made up of bundles of superconducting and coppers strands that are cabled together and contained in a structural steel jacket. I'm sure you are familiar. The superconducting coils are mainly ceramics. They are fragile, and if you don't put them in a jacket and even in a casing, they will just be tearing apart. And indeed, we need to set up a unique worldwide collaborative procurement involving effort involving China, Europe, Japan, Korea, Russia, and the United States to the production of some 200 kilometers of superconducting cable. And due to the ITER need, you have to think about that the niobium tin strand production capacity has grown up from less than 15 metric tons per year to over 100 metric tons now. The big challenge, as I explained to you, is we are moving and manufacturing pieces which are more familiar in a shipyard, several hundred of tons and size of more than 10 meters. And you see it is the assembling piece we are working on, but with a precision of a watch-like activities. And for example, I am pleased to say that this year in March, at the Mitsubishi facility in Futani, Japan, the winding pack for toroidal field coils was successfully inserted into its steel case within 0.2 millimeter tolerance. The case is made up of 2 pieces. You have to fit the 2 pieces with this tolerance, and I am pleased to say that now we succeed and we are producing the 18-1 the same way. So, maybe you are aware, the project has a slow start. Indeed, many difficulties because it was no clear management rule. In particular, it was like a UN forum. Everybody has his words to say. No decision without consensus. Not to speak, it's not possible. So I was requested, as François said, after I finished my term at the CA, to consider this project. I was associated with, from the very beginning, and I proposed a clear action plan, and the most important one is that we decide that the ITER organization Director General had full capacity to decide. Everybody has to comply with his decision. If you are not pleased with the decision, fire the DG, but as long as he's in charge, accept his decision. And so it is in this condition we have made a review of the project, and it has been agreed in June and November 2016 to have a new schedule, a new organization, a new cost also. First plasma is supposed to be delivered in December 2025, and first nuclear plasma with full fusion power 10 years later. We will start with our first physics experiment in 2028, but it is the schedule. And we could not do faster. There is so many activities which have to be checked properly that it is not able to do that. So since 2016, once the ITER Council has approved our schedule, we are on time. We are absolutely month per month on time. And I am pleased to say that we see that this year and the next 2 years we will collect all the large components worldwide on site to assemble them. And again, if you are free on late December 2025, please join us to have the first plasma. We hope so. After that, due to the limitation of resources from the different countries, we will have what we call a stage approach, where we'll assemble some extra components which are not needed for the first plasma, and offer to the physicists the possibility to start learning about this machine and starting to have some experiment. And you see, we will have full fusion power at the end of 2035. So now, just a few slides to show you what we call the work site. So again, it's an aerial view. Here is the tokamak building. At the center, we have this huge, what we call bioshield wall, which will protect the workers and the environment of any neutron which could escape. You have to think about that we will produce billions of neutrons per second. Everybody which knows about the Avogadro number could consider that. And so even if we collect most of them, some of them could escape, and we need to protect. So this building is concrete, is 18 meters deep in the ground, on a huge slab, 120 meters long, 80 meters large, on nearly 500 anti-seismic bars, in such a way that if there is any move, we will not disassemble the tokamak, as I explained to you. On each side here you have what we call the diagnostic building, where we will collect all the information on the tokamak functioning, and on the other side is the tritium building, where we will recycle the component. 2 cylinders and a top lid. The base is nearly 1,300 tons, and it will support all the equipment. It is 30-meter diameter. The lower cylinder is 10 meters high. It is finished, and we put it out of the workshop because we need space, and we cocoon him. We have put a huge foils in order to protect it for nearly 1 year and a half before we could put it on the tokamak. And you have to think about where we have to assemble these 2 pieces, 2 circles, 30-meter diameters. Thickness is nearly 5 centimeters steel, and it has to be well with a precision below a quarter of a centimeter. Again, also on the site, we are winding the huge coils. The smallest one, there is 6 horizontal ones. The smallest one is wind in China and in Russia, and the 4 largest one, which will go up to 24 meters, could only be manufactured on site. Indeed, this one, which will come from China very soon, is 10 meters, and we expect that we will succeed. Now, you have the heat rejection system. As you see, it's quite large and significant, and we are on our way in order to deliver it. Electrical network, I'm sure you are interested in. As you see, here is the switchyard. Indeed, some people could understand it is Réseau de Transport d'Électricité in France. We have it. It's large enough in order to accommodate a town of 3.5 million of inhabitants. Because when we will start the plasma, when we will get all the magnetic energy from the coils, we need to have 600 megawatt of power for 1/10 of a second. But I need it. We have a lot of transformers and the converters and we are pleased to say that now we are connected to the grid and we get our power for that. We have 2 systems, a steady-state electric network, total power to be distributed around 120 megawatt continuous, which is about twice that of a 1.4 gigawatt nuclear power plant. And you see the main consumer, a cooling water system, cryoplant, building services. And you have what I call the pulse power electrical network, with a 2.2 giga volt amperes, connected power converters, and the main consumer clearly are the coils. So we are making that. Now we are on our way to assemble all the components in 2 large buildings, which are ready. We take over them very recently, and you see we will have after to connect this converting building to the tokamak through a 50-meter long bridge with both the electrical devices as well as the bus bar. I know your meeting is Jicable, okay, and so if you enjoy to see some cable, just come and see us. We are nearly 200 kilometers of cable tray, 120,000 cable, 10,000 kilometers of cable, and you see with very strict specification in order to be able to get the full approval of the what we call the nuclear regulatory body. And for example, you see we have made a lot of trial by fire in a dedicated facility. Not only we have this superconducting coil, but we have also what we call the bus bar. The bus bar, there is nearly 10 kilometers of bus bars. They are copper bus bar, and you see the maximum cross-section is quite significant. And the bus bar are now on site, and I am pleased to see last week we start their installation, and we expect to be ready on time for that purpose. So again, as I explained to you, all the members have decided to split and to break down the procurement, and you see the feeders, the cable, in order to connect the superconducting coil is from China. But all the toroidal field coil, everybody wants to have a piece, and indeed nearly 6 partners have developed it. Okay, the other coils the same. Okay, the central solenoid is Japan and US. The diverter which will collect the helium is Europe, Russia, and Japan. The blanket module which will collect the neutrons is China, Europe, Korea, and Russia. And for example, the cryostat is India. So you see everywhere, as I said to you, we are now moving up in order to complete the manufacturing of all these different equipment. In China, for example, as I explained to you, one of the coils, the PF coils, which will come on the site by next September. In India, they procure the cryoline, which will feed in the helium in the coils. In Europe, they are manufacturing the sector, the vacuum vessel chamber. In Japan, they are processing some cold test in order to be sure that we are fully qualified. Korea is also manufacturing some other piece of the vacuum vessel sectors. Russia is moving up with the coils, and the US central solenoid. So all of them are moving properly. And I want just to give you some recent highlight. We expect that on next 23 July, we will celebrate with ITER India the completion and acceptance of the cryostat base and lower cylinder. And this is a lower cylinder, as you see when we move it away from the workshop. Here is a workshop in Italy where many of these components will be assembled in order to procure the vacuum vessel. Italy, Europe, indeed, with a large European consortium, including Germany, Spain, France, Italy, and many other nations, are procuring 5 of the coils, while Korea is procuring 4 others. And in Korea, we are at the stage, we are assembling the fourth piece of the vacuum vessel chambers. Each of these pieces is nearly 150 tons, and you see they have set up a huge table, and with cable and all these things, and very precise metrology, I hope they will be able to assemble and to deliver by next December. Here is what I call the ITER J-well. Indeed, it is a silver plate vacuum vessel thermal shield, like in space, in such a way that between the vacuum vessel, which will be nearly 200 degrees with the water flowing in, and the superconducting, which will be minus 269, you have a protecting system. And you see is stainless steel plated with silver. Now we are moving on in order to have the crane, which will be able to lift 1,500 tons and position the equipment. And there are the pillar, which will be above the tokamak building in order to expand the assembling hall. And we are moving. In Cadarache, we are finalizing what we call the double pancake for polyol field coils, which are completed recently. China has spoke already. They will celebrate very soon the completion and preparation for shipment of this polyol field coils. I just repeat the very great achievement. Indeed, is like a landmark when with specific technologies, Japan, has been able to assemble the first winding pack in their case. And it's a good illustration. Europe has also to do some of this casing for the toroidal field coils, and they decide to do another way. And my predecessor has accepted that. So I need to qualify the two processes. I need to follow the two processes. But it is a research facility, and maybe in that way we will know what is the best way to proceed. Okay, now we are moving from fabrication to assembling. We are preparing the assembling. And again, for example, we have made a huge mock-up with robots in order to demonstrate we are able to weld the vacuum vessel sectors. The 9 pieces of the vacuum vessel sectors I mentioned is like orange piece. And again, I repeat to you, we have to assemble all these pieces in such a way at the very end. The magnetic axis of the magnetic cages with the coil fixed on these vacuum vessel sectors will be within 0.5 millimeter. Okay, now we have a lot of heavy load coming from all over the world. They join us through the Marseille Harbor. They cross over the Étang de Berre. I don't know if you know near Marseille. Okay, and after that, during 3 days, indeed 3 nights, because we don't want to disturb the local traffic, okay, at a speed of 5 kilometers, with a lot of indeed police walking around, because I don't want any damage to this component, which took for some of them nearly 6 years to be manufactured, be damaged. There is quite a large, significant economic impact. Right now, we have passed more than 9.5 billion euro in contract for construction and fabrication. The estimated cost for the construction is 20 billion euro, okay, and is why all these partners need to associate. Right now, at the work site, and again, this picture is quite old, we have nearly 2,300 workers, and very soon we will be, 3,000. ITER, as I mentioned to you, is just a research facility, but it is an ITER, you know that in Latin means the way. Is you have to go through ITER if you want to succeed and have a fusion power plant. So ITER is on its way, and we hope we will be succeeding. And already, several countries are thinking of what they call demo, the real industrial demonstration to be connected to the grid to produce power. Europe is already thinking about that. It's just a sketch of this, and Europe demo would produce between 300 and 500 megawatt of electricity. We are producing it just now. So I hope I convince you that ITER is moving forward. It's quite a challenge, but be sure that we are dedicated to make this dream a reality during this first part of the century, to have a large industrial development later on. Thank you very much for your attention.